Hey everyone, welcome to week 10 of a recorded mini lecture. This week we'll be covering reduction. So this will bleed a little bit into the content coming up in the next couple of weeks, but this idea of reduction is definitely not new. We've alluded to this a bunch of times in lecture as well as on exams. So I hope this is a, I guess, good unifying lecture that you're gonna, feel good about your knowledge of previous content as well as future content after this. So let's get started. The reduction follows this theme that we've been appealing to for the past couple of weeks, that we're building a repertoire of problems, that we're building a list of problems that we're familiar with and we know how to solve with an efficient algorithm. And now when someone hands you a new problem, you're tempted to go down the list of the old problems and see, do I have an old problem that solves this new one? So in this mini lecture, we'll make slightly rigorous this idea of using a problem to solve another problem, and be able to start talking about the idea of one problem being harder than another, or one problem reducing to another. Regardless, this will eventually give us the language to talk about difficulty of problems, and eventually give us some mechanism to talk about P versus NP, the greatest problem in computer science, many would say. So I hope you're excited for this. This is one of my favorite, one of my favorite things to think about in 170. So let's get started. I wrote down this motivating example at the beginning. This is a little bit of a silly example, but I hope it gives some illustration of what we're talking about here. So if you remember, a couple weeks ago, we devised a shortest path algorithm for directed acyclic graphs, or DAGs. I encourage you to pause the video now and think about what that algorithm was that we developed a couple weeks ago. So pause. All right. Hopefully you've paused and thought about this. I won't be going through it because today we won't be digging through the graphs and edges and edge weights at all. So, all right, so suppose, I devised that algorithm in the second morning. You wake up and you really want to find the longest path. And you're thinking, these problems are similar, but you might be thinking about, getting real deep into the nitty-gritty of that algorithm, looking at updating lengths or whatnot, and thinking about how to make that fit for finding the longest path. However, I propose that there's a way to do no work at all and to not look at the graph at all. So this algorithm that I've written here, func longest path length, calculates the longest the length of the longest path in a directed acyclic graph G. And now I say that all I want to do in this algorithm is I can negate all of the edge weights of G. So now really long paths become really negative, so they're going to be really small in weight. And really short paths are going to be less negative, so they're going to be longer. We've essentially inverted the idea of long and short. And now I'm going to run shortest path length on this modified graph G, G prime. And now I'm going to get a path with the shortest length. And I'll remind you that now, because we've modified this graph, the idea of short just means really, really negative. And thinking about the graph before we modified it, this means that the absolute value of this length, the path lengths, are going to be really, really large. So now this, as you can imagine, this is going to be our longest path. And all we have to do is negate this really negative length and return it. So now it's this very large positive length, and we found the longest path. I encourage you to think about why this works. And the idea is just, we want to find the longest path. And now, we switch the idea of long and short by negating edge weights, and now our problem becomes finding the shortest path. So this algorithm works, and what you want to notice is that we're really not lifting up the hood to the graph. We're talking just about nothing in terms of going vertex to vertex, edge to edge. All we have to do is update edge weights, run shortest path, and then negate the result from that calculation. And so we call this, this intermediate algorithm that we've used, we call this the subroutine, right? We've seen this language before. And we call the stuff that you do beforehand, we call this pre-processing. it's like you're processing this graph G so that you can feed it into your subroutine. And then now, after I've done my subroutine, I'm going to post-process, and this post-processing will ensure that what I got from my subroutine can be adapted to this problem that I'm solving in the first place. So these are the three ingredients to any reduction problem. You're going to pre-process, run a subroutine, or this is the problem you're reducing to. I'll write this down. Problem we're reducing to. All right, problem we're reducing to, and this is afterwards we post-process. And at this point, we can say that we've reduced longest path to shortest path. And I'm talking about these as like problems. I've reduced the longest path problem to the shortest path problem. All right. And so this makes sense, right? Because by reducing, we started with no algorithm for longest path, and now we have an algorithm. So that's great. We love this. We want to do this for many, many problems because, as you can see, that we have in the past sort of problem repertoires that we've developed, we have these fairly general tactics or fairly general techniques that we've just built up. And now we want to use these general techniques to solve a large class of problems. And the idea of reduction gives us a formal way to do this. And this should remind you of something else. Maybe this should remind you of linear programming, that when you're handed a problem that isn't really very glaringly linear programming-ish, you're formulating it in a linear programming way. And then by solving the linear program, you actually get a solution to your problem in the first place. And you can think of this also as zero-sum games, right? The way we solved zero-sum games and the way we solved max flow are both through linear programming. So in lecture, we never talked about, we reduced one thing to another, but now we can use this formal language to say we reduced zero-sum games and flow to linear programming, right? So this idea is very powerful, that with you can put a lot of things in this blank right here that you can reduce to linear programming. All right, so now let's do some formal definition, or I guess a little bit of abstract definition, where I say I take a problem B, and if it reduces to problem A, I have the following diagram, right? If we're reducing problem B to problem A, I better have an algorithm for problem A so that I can solve problem B with, right? This is essentially, it's following the same logic as before, and now I have a problem B instance, and I want to, I have a problem B instance, I want to pre-process to make it into a problem A instance, and I feed this problem A instance into the problem A algorithm that should give me a problem A solution. And using the solution, we should post-process and get a problem B solution. And so through this sort of roundabout manner of going this way down and then this way, we've essentially gone from a problem B instance to a problem B solution. And ultimately that's what we want, right? And the bread and butter is that we have a problem A algorithm. Now, on the other hand, I think this is a similar illustration. It just depends on which one works for you. It's completely up to you. That you can also think of this as I'm building a blue box for the algorithm for B using the box for A. So what I'm doing here is I have a problem B instance X passed into this box, and I go through pre-processing, I pass it through the algorithm box for A, and I post-process, and I say that the middle three steps as a whole is an algorithm for B. And now in the end, I get a solution to B. So these are just two different ways that you can think about this entire idea. So I encourage you to pause on the screen and just convince yourself that this really works, that this is what it means for problem B to reduce to problem A. Make sense of this, and we'll get to some very confusing logic very soon. All right, pause. All right, I hope you've paused the video. Now you're back. Guys, this is really weird. I'm just talking into a screen and I'm hoping that you've paused the problem and convinced yourself that everything works. Regardless, so let's look at what it means for problem B to reduce problem A. I've written a bunch of really confusing statements, or I guess maybe not so confusing if you understood this well. But you might imagine that you can already see things like this coming up on the midterm or final, where I say, okay, which of the following is true if B reduces to A? You might be given some statements that look relatively reasonable, and then they might have just switched up the letters A and B, and you would not know how to how to actually handle it. And so this is a problem I faced when I was taking the class. So I wanted to really drill this in, like, what does B reducing to A mean for these problems? What does it mean for their difficulty? What does it mean for their the logic in their algorithms? So let's dive right in. If B reduces to A, then we're using an algorithm for problem A to solve problem B, right? Because B is the thing we want to solve eventually by reducing to a familiar problem. All right? And so the second statement is we're turning B into an instance of A. That's also true, because again, B is the problem we want to solve through A. All right? Now the next one's a little bit weird. A is at least as hard as B. Think about this for a moment. Pause the video and think about if this is true and try to convince yourself of this. Okay, so the way I like to think about this is the following. If there's an algorithm for A, then there's an algorithm for B, we've established, right? Because in this diagram, if this A exists and I can do pre-process and post-process successfully, then I have an algorithm for B. So if there's an algorithm for A, then there's an algorithm for B. The converse is not true. I can't go backwards. Just because I have an algorithm for B doesn't mean there's always an algorithm for A. You can think of this as using a silly example. For example, I can reduce the problem 1 plus 1 into the general theory of algebra. Right. And I can do this. This really reduces to this problem because, if I have a general theory of algebra and I know, or arithmetic, whatever you want, or, all of mathematics, whatever you say, if I have this general theory of algebra and arithmetic and I know how to do everything, then I must also know how to do 1 plus 1. But it's not true otherwise, right? Just because you know how to do 1 plus 1 does not mean that you know all of arithmetic or algebra or all of mathematics. And so this, I think this statement right here, this if there's an algorithm for A, there's an algorithm for B, it should be intuitive that it doesn't go the other way around. All right. So then this problem, I guess this idea gives you a justification for why A is at least as hard as B, right? It's saying that, if I can solve A, I can solve B. So A must be, as hard as B, right? Like, or harder. A could be harder than B. If there's an algorithm for a harder problem, I better have an algorithm for this easier one as well. All right. On the other hand, if B is unreasonably hard, we expect that A is too. And that just comes from this idea of, A is at least as hard as B. Right. So realistically, you only need to remember one of these statements to deduce the rest, but just make sure you really understand which way this goes, because you could imagine, I'm going to pull up a different screen, and I'm going to pause here and ask you, okay, if I reduce problem A to problem B, if I reduce problem A to problem B, okay, listen carefully. If I reduce problem A to problem B, then problem A is harder than B, or at least as hard as B. Is this true or false? Pause the video and think about this. All right, I hope you're back. This is false. Do you see what I did there? I switched it up. I reduced A to B rather than B to A. So you can see that this is, yeah, it could get very messy very quickly. But assuming that everything here makes sense, let's, I don't know, just drill it in one more time that B reduces to A means A is at least as hard as B, and it means an algorithm for A will give an algorithm for B, and we're turning B into the problem, an instance of problem A. All right, hope this wasn't too confusing. I hope you're still feeling good about this lecture, and I'll see you in the next segment. All right, so I want to give a couple words of caution on this entire idea of reduction, because in the previous segment I was in optimistic mode about reduction is awesome. If you find some problem to reduce to, you should feel very happy and whatnot. But now I'm just gonna say that there's a bit of I don't know caveats there. That first of all we want efficiency of pre and post processing. That from this previous diagram that we drew, the runtime of this arrow right here is dependent on every single segment in this three-part process. And we just sort of assume that, problem A algorithm is going to be the one that dominates. So what we really want is for the pre-process and the post-process to both be relatively efficient. For the most part, we ask for them to be polynomial time. And this is, in light of P and NP, but sometimes we ask for more. For example, if problem A algorithm is a constant time algorithm and you use like a super exponential time pre-process, then you've basically screwed yourself up. And so in general, we just want to make sure that pre-process and post-process don't overtake the problem A algorithm. The second thing is making sure that the instances still fit basic requirements. This is what this means is once I pre-process, I want to make sure that the result of my pre-process is a valid input into the algorithm for A, and that the output for A can be, reasonably post-processed. So I guess some things to check for is, for example, if my algorithm for A is an algorithm for directed acyclic graphs, then I better not be passing in some cyclic stuff into it. Or if the algorithm for A only takes care of positive edge weights, for example, using Dijkstra's, then I better make sure that after I pre-process, I don't have any negative edges. So these are sort of things to watch out for in order to make sure that the inside of algorithm for B still works out once you've done your reduction. And the last thing is picking a good problem to reduce to. This one is, I think this is going to be the bread and butter for the next couple of lectures and next maybe couple weeks of lecture and even the final project. It's that, you want a problem that's solvable, but more importantly, you want a problem that's solvable efficiently. So suppose, I have the silly example that I took was you take 1 + 1 and you reduce it to some crazy problem in algebra or arithmetic. But it's true that you could have, some, I don't know, you could have some very easy problem B right here, and then you reduced it to a hugely impossible problem A or something that's just gargantuous or whatever it is. So make sure that when you're thinking about these problems in discussion, homeworks, and going forward in doing the project, think about what kind of problems is good to reduce to, and there's an extra layer of you want the pre-process and post-process to be relatively smooth, right? So that's all there is to, all there is to know for this particular lecture, and I'll pass it off to Neil, and then afterwards we'll have a couple of tutors giving really classic examples of reduction. All right, thank you.
Thanks, Lily. In this video, we're going to be covering a few examples of search problems. And so basically in 170 so far, we've studied a ton of different problems that have really efficient solutions, right? For example, like dynamic programming or various graph algorithms. A lot of these algorithms have like very neat, polynomial efficient runtimes, right? For example, n log n or n squared. But there's an entire class of problems that don't yet have like efficient solutions, right? So there's an entire list of problems that have exponential algorithms, right? And so for us, we don't want, we kind of define an efficient algorithm to be something that runs in polynomial time, whereas inefficient algorithms or really hard problems to solve will have exponential runtimes, right? Their algorithms will be, the amount of time it takes for those algorithms to run is going to grow exponentially in terms of the input that they get. And so the key word is, yet, because there's a lot of research that's currently been, going on in this field, because it would have like huge ramifications in terms of like research and applications if we were able to solve more efficient, ways to solve some of these hard problems that we don't have good answers yet. So before diving into some specific examples of some of these problems, let's define what exactly a search problem is, right? And so a search problem is any problem where once you're given a solution to that problem, you can easily verify whether that solution is right or wrong, right? It seems like a very trivial definition, but let's go over an example. So take a look at this slightly ugly graph, but let's say you have this graph and you're starting here, and you're starting at this point and you want to end here. You want to drive over there, right? Let's say you have a car with a limited amount of like gas, right? Let's say you have 10 gallons in the tank, and you want to find, your problem is you want to find a path through this graph such that your car will actually make it, right? You want to find a path that uses less than 10 gallons of gas. And so again, going back to this definition where it's like, given a solution to a problem, you can easily verify whether it's a valid or invalid solution. So let's say, for example, in this problem, someone gave you a proposed path, right? Someone told you to take, I don't know, let's say this edge, then this edge, then here, then back here, and then here. And if you do the math, I think you'll get 5 plus 4 plus 1 plus 3 plus 2 plus 1. That's going to be, I don't know, some number bigger than 10, right? So you can easily verify that that path is going to be, is not valid, right? You're not going to have enough gas. Whereas if someone else gave you, I don't know, let's say just using this edge and then this edge, that's going to be 5 plus 1, which is 6, right? So given that path, you can say, hey, this path is a valid path. It works. It's a valid solution, right? So that's what I mean when I say, you can easily verify if a solution is valid or not. It basically means that once someone, looks at the problem and gives you a solution, in polynomial time, you can verify that, you can check whether it's a good solution or it's a wrong solution. And so keeping that definition of search problems in mind, let's go over a few examples of different search problems. Some with some problems that we have good algorithms to tackle, and some that we still haven't discovered good algorithms to tackle. And the first one that I want to cover is SAT, which is short for satisfiability. And so you guys have seen something like a variant of the SAT problem in chapter 5, I think, with the Horn formulas, with greedy algorithms. So this is kind of like more of like the general version of that problem, right? It basically says, you have expressions, you have like a bunch of these expressions and a bunch of variables inside those expressions. And inside each of those expressions, you have these variables separated by like OR operators, right? And you want to find Boolean assignments to all of these problems. And by that, I mean like you want to find, assignments where you assign each variable to either true or false. So you want to find these Boolean assignments such that each of these expressions evaluates to true. And so a way I like to think about it is you can think about each of these expressions kind of separated by an AND operator, right? And you want the whole expression, the whole kind of problem to evaluate to true, right? Because then what that like necessitates is you need this expression to be true, this expression to be true, and this expression to be true. But then inside each expression, since they're each, kind of like separated by these OR operators, inside each expression, you just need one of the values to be true, right? And so, for example, I think a solution to this problem would be if you set X to true, Y to true, and you can set Z to, I don't know, false, for example, right? Because, so then if X is true, so let me just write those down. X is true, Y is true, Z equals false. I literally just came up with this assignment like on the spot. So if you check whether, let's see if it's actually valid. So if X is true, then this expression will be true. So that's good. If X is true, this expression is also going to be true. So that's good. Now going on to the third expression, we know that Y is true and Z is false. So since Y is true, this third expression is also true. So now you know that all the expressions are true, which means you found, this is a valid solution to the problem, right? And so this is basically what the satisfiability problem states. And I kind of answered my next question, but given a proposed solution, can we verify if it is correct in polynomial runtime? And so as you saw, like, I just came up with like a random, assignment, random Boolean assignments for each of the variables. And we were really easily able to check whether, those assignments worked for our satisfiability problem, right? All we did, we just plugged and chugged. We checked if the assignments will all yield true expressions. And so it kind of checks this problem off. Yes, right? There's a really easy way to check. You just plug and chug. And so that's why the satisfiability problem is a search problem, right? Kind of going back to this definition. So it turns out there's variance to the SAT problem, right? So if you limit each of these expressions, to having less than or equal to 2 variables inside of them. So an example of that could be like, let's say you have X or Y, and you have like Y or C, and then you have like not Y or C. You have like some of these expressions, right? If you can limit the number of variables in each expression to being less than or equal to 2, that variant is called 2SAT. And it turns out 2SAT has an efficient algorithm, right? The algorithm we use to solve 2SAT is an efficient one. It runs in polynomial time. And as you saw, the variant of this problem using like Horn formulas in chapter 5, that also had an efficient algorithm, which was, just a greedy algorithm, right? It had an efficient polynomial time algorithm. But it turns out the moment you make this 2 into anything greater than 2, right? For example, 3SAT. So 3SAT is the same problem. It's just each expression can have up to three variables. So it can be like X or Y or C, and then Y, X, Y. And you can have like a ton of these expressions. So the moment you change the constraint from 2 variables per expression to 3 variables per expression, this becomes intractable to solve. We don't have a good algorithm to solve this. The easiest algorithm that we have, or that you can come up with, is like the brute force approach, right? Going through all possible Boolean assignments, which is going to be exponential runtime, right? And we don't like exponential runtime algorithms, right? Those are intractable. Those are really inefficient. So turns out like this minor difference is enough to change a problem from easy to solve to completely super difficult to solve. Yeah, so that's with satisfiability. Let's go on to the next search problem, which is called the traveling salesman problem. So here, our task is, it's actually really similar to the kind of dummy example I gave here with the car and the gas. So it's basically saying that, let's say you start off at this vertex, you want to find a cycle that passes through all the vertices in a graph exactly once, right? So it touches each vertex exactly once, such that your total cost of your cycle is within some predefined budget, right? So in the previous, in the problem that I just covered like earlier, that budget was like the number of gallons that you have in your car tank, right? But it's basically like you're trying to find a cycle that, is within this budget.
So for example, if you have, if you predefine your budget to being 25, right? Going through this example, let's say going through, this graph, let's say someone proposes a solution that is, simply, oops, simply, let's say someone proposes a solution to simply go around the edges of the graph, right? The, surrounding edges of the graph. So to verify that that solution is actually valid, all we have to do is, literally go through the edges, make sure that it's a cycle that passes through all vertices exactly once, and also make sure that the total cost of it is within our budget, right? So if we do that, we start from, this one, we add a cost of 3, we add a cost of 5, 3, 2, 6, 3. So that would be 13, 22. Your total budget, the total cost of that path is 22. Is it a cycle? Yep. You're starting and ending at the same vertex. And are we covering each vertex in the entire graph exactly once? Yep. You're covering, you're starting from here, you hit this one, this one, this one, this one, this one. So you're not, you're covering each vertex exactly once. Your cost is 22, which is within our total budget 25. So yeah, it looks good. We found a solution, right? So again, I went through that, basic example to kind of reiterate the concept of like a search problem, right? So the traveling salesman problem, the TSP, it is a search problem because once you're given a proposed solution, which in this case like is some cycle in the graph, verifying that it's actually a valid solution is pretty easy, right? You can do it in polynomial time by literally just walking through that proposed solution. And so, yeah, that's kind of like what the TSP problem is. But there is a slight variant to the problem, right? And it comes around this notion of the budget, right? So what if we got rid of this concept of the budget altogether? Instead, what if our problem was we had to find the cheapest cycle that passes through all vertices? So there's like a subtle difference, right? In this problem, what we're given a predefined budget. All we have to do is find any cycle that has a cost less than this budget. Whereas in this problem, we're trying to find, of all the possible cycles, we're trying to find the cheapest one. And so when I first introduced the TSP problem, like, why did I start with this definition? Why is this definition the one that's used for the TSP, for the traveling salesman problem? And it's because of the definition of a search problem, right? Again, for a problem to be a search problem, we have to easily verify whether a solution is correct or not, is valid or not, right? And the moment we get rid of the concept of a budget, it becomes significantly harder to verify that a proposed solution is right. And the reason that's the case is, in this case, in the original definition, we're given a budget, we're given a proposed solution. All we have to do is run through it, make sure the the cost of that cycle is within our budget. Whereas in in the modified version, in the kind of optimization problem version of this, if someone gives us like a cycle, right? What we can do is we can go through the cycle, make sure that it passes through all vertices exactly once, and then calculate the cost of that cycle. So let's say, again, let's say someone proposed a solution, the same solution, kind of going around all of the external vertices, external edges. And so what we can do easily is we can come up with the cost of that, right? And so the cost of that cycle is, as we calculated before, is just going to be 22. But the thing is, in the first case, in this definition, it was easy to verify. Yep, 22 is less than 25. It's a solution. But in this in this framework where we don't have the concept of a budget, we're just trying to find the cheapest cycle. How do we know that this cycle of cost 22 is actually the cheapest cycle? There's no good way of finding out. Who knows? There could be a ton of other cycles in this graph that have way a way lower cost, right? So just because you're given a cycle and verify that, just because you're given a cycle and can calculate the cost of that cycle, there's no telling like whether it's actually the cheapest way of doing this problem, right? And so this definition, this framework, is not really a search problem. It's more of an optimization problem, right? Because there's no easy way of verifying that the solution is actually the correct cheapest cycle. So yeah, that's kind of like the difference between the two problems. Like, you know, be very careful in your kind of like the way you frame problems to make sure that it fits like what we mean by a search problem. Yeah, it turns out both of these problems are computationally very expensive to solve. There's no good efficient way of solving these problems. And so two more problems I want to cover. So the first one is called the Euler path problem. And in this problem, what we're trying to do is we're trying to find a path between two vertices in a graph that contains each edge in the entire graph exactly once. And so a simple example of that is, you know, this graph on the right. Let's say we're trying to find a path from A to B. And so an Euler path is going to be a path between these two vertices that contains each edge in the entire graph exactly once. And so here, that path is pretty evident. You kind of go, you choose this path first, and then this path, and then this, this edge first, then this, and then this edge. So, you know, this path uses each edge exactly once in the entire graph, and it returns a path from A to B. So that's like an Euler path, right? But if we're given this graph on the right side, you can kind of like think about like different paths from A to B, but what you'll realize is there's no path that gets from A to B exactly once. There's no path from A to B that uses each edge in the graph exactly once. And you can try it, right? You can go from here to here to here, but then you've gotten from A to B, but you're missing this edge. You can go from here to here. You've gotten from A to B, but again, you're missing this edge and this edge. So yeah, you can kind of play around with it, but you'll realize that there's no like, this graph doesn't really have an Euler path, right? So yeah, that's kind of like the problem of an Euler path. It's basically find the path and return it. Again, it's a search problem because given a proposed solution, given a proposed path, you can easily tell that whether it uses each edge in the graph exactly once. Now, a very similar problem is called the Redrata cycle problem, right? In this problem, we're trying to find a cycle in a graph that visits each vertex exactly once. And so as you'll notice, right, there's very few, it's basically the same as an Euler path with two differences. The first is in the Euler path, we're trying to find a path, whereas in the Redrata cycle problem, we're trying to find a cycle. And the second difference is in the Euler path problem, we're trying to find a path that contains each edge exactly once, whereas in the Redrata cycle problem, we're trying to find a cycle that visits each vertex exactly once. And so, as you'll kind of like notice, the Redrata cycle problem should kind of ring a bell. It's very similar to, you know, the TSP problem, the traveling salesman problem that we covered here, right? Finding a cycle that covers each vertex exactly once, except here we kind of had this like whole budget thing, the budget factor to the problem. But anyway, the Redrata cycle, you know, it's similar to the TSP problem, and yeah, so as it turns out, the Euler path problem is, we have a really efficient way of solving it, right? We have a polynomial time algorithm to finding an Euler path in a graph or returning that one doesn't exist. But then the Redrata cycle problem, as I mentioned, it's similar to the TSP problem. And as I said earlier, the TSP problem is computationally, you know, infeasible, right? It's an intractable problem. It's like the best solution that we have is an exponential solution, right? And so the Redrata cycle is also, you know, it doesn't have a good polynomial runtime algorithm to solving it, right? So the Euler path is super easy to solve in terms of like, not in terms of like, you know, coming up with the algorithm, but the algorithm itself to solve the Euler path problem is polynomial, right? There's a really efficient way of solving it. Whereas the Redrata cycle problem, we don't have there's no known efficient algorithm. Maybe someone will discover it sometime in the future, but as of now, there's no known efficient algorithm. And so I kind of wanted to like include this last example of like an Euler path versus Redrata cycle problem, because it really emphasizes the the effect that a really small difference in a problem statement can make in terms of like how easy it is to solve it, right? Because the only real difference between both of these problems is the fact that the Euler path looks at edges and the Redrata cycle looks at vertices, right? The whole even the difference between like the path and the cycle, like if you think about it, a cycle is essentially just a path from like a vertex to itself, right? It's more of like a it's not really like a legitimate like huge difference between the two problem statements, right? The main difference between these problems is that like one is looking at the edges, one is looking at the vertices, and that minor difference makes like the world of a difference in terms of like how efficient each algorithm is going to be, right? Euler path, we have a good algorithm of solving it, and then the Redrata cycle, we don't have a known efficient way of solving it. So yeah, those are some examples of search problems. I just wanted to cover a few of them, and kind of like giving an overview of like the next few weeks. We're going to be looking at various search problems. Some of these, the ones that we covered, are the traveling salesman problem and the Redrata path, which are harder problems that we don't have good algorithms of solving. Also the 3-SAT. But then, some of the other problems that we have good, algorithms of solving are the 2-SAT/4-SAT, which are like kind of like variants of the satisfiability problem, as well as, let's see what else we looked at, Euler path. Okay. So yeah, keeping those problems in mind, what we'll study in next week is how we can go from one problem to another in using the concept of reductions. But until then, good luck with the homework. See you guys next week.
Hi, everyone. Welcome back to 170. Hopefully the midterm went well for everyone. So today I want to go over reductions, which is what we're starting. Post-midterm 2. It's awesome. Great unit. And I just want to go over a reduction problem with three-dimensional matching, because I think it's a good example of showing the intersection of many NP problems. So I think not everyone knows what NP problems are, which is totally fine, but just a little bit of intro before you go over it in lecture more extensively. NP stands for non-deterministic polynomial time in CS theory, and it's for problems that have no known polynomial time solutions. For example, there's a traveling salesman problem, 3-SAT, longest path, Euler's tour. But if we're given a solution to this problem, we can check that it is correct or not in polynomial time. So you've probably seen memes about P equals NP floating around, and if you haven't understand them, you will in no time. So we will be covering them in the future or in the next chapter. So such as like proving a problem is NP or NP, or like reducing NP problems to each other, etc., etc. But for now, let's just work on building some intuition and finding and utilizing the relationships that different algorithms and problems have with each other. Without further ado, let's jump into our first reduction with 3D matching. So this is actually from your textbook on page 256 of chapter 8.1. And they left an exercise for the reader to understand why 3D matching is also a special case of set cover. I know I'm throwing a lot of terms at you. There are a lot of names that are given to these different problems, so definitely get familiar with them. Also, like very helpful to put on your cheat sheet, like just the problem statements and existing algorithms or solutions maybe. But first, let's just make sure we're on the same page. So let's define 3D matching. Actually, let's cover 2D matching first, just to jog everyone's memory. So in bipartite matching or 2D matching, we have two sets, X and Y, they're disjoint, and each with size n. So we are also given another subset that is the Cartesian product of x times y. So what that means is that, so the Cartesian product is you take every element in x and then you pair up with every other element in y. So you end up with what? That's n squared elements. So you're given a subset of that, which indicates compatibility or like a matching pair. So if you're not like matched with someone in the other set, then there's no, then you're not part of this given subset of the Cartesian product set. Okay, that's a lot of terms anyway. So this is sort of like stable marriage, except without like a ranking. That's very complex. I don't want to go into that. But also something I wanted to point out is that elements in the same like set, so elements in X cannot be paired with each other. So think about this like as a zip function in Python. Also, I know that like many of you know this, but I just wanted to confirm this before we build on top of it with 3D matching. And the question, of course, is there a set of exactly n pairs in this given like Cartesian product? So let me just name it so I don't have to keep on repeating it. Let's call it T. And this is a subset of, yeah, the Cartesian product. So let's say, is there a set of n elements in T such that every element is contained in exactly one pair? By element, I mean every single like member of each set. So is there a pairing such that all 2n elements are happy? Right? So as you've seen from your last chapter, we solved it with max flow. So obviously bipartite matching is actually in polynomial time. But once we expand that to a three-dimensional matching, very surprisingly perhaps, it goes to, and it becomes an NP problem. And just to allude to some other examples, for example, the 2-sat problem is in polynomial time, is since remember like we solved it with the Horn formula, but when you expand it to 3-sat, it's NP again. Similarly with 2-sum, which you can solve easily with the hash map data structure, but if you expanded it to 3-sum, things just get crazier once you like add a variable, and we're no longer in polynomial realm. Yeah. So just to define three-dimensional matching, like formally, let me just add on to this 2D matching definition that we have. So for 3D matching, we have another set over here. There's also exactly n members in here. Instead of 3n, instead of 2n, we have 3n total elements that we want to satisfy. And let me just visualize this so it's better for everyone to see it. And there are edges connecting it over here. Yeah. Instead of 2-element tuples, you have to look at 3 at a time. And the question is there a set of n triples or triplets in this T subset such that every element, each of the 3n elements is contained in exactly one triplet? And of course, they have to be contained in some triplet, but exactly one. This is our definition of a perfect 3D matching case. So let's just look at that in a graph example, because I believe your textbook converts that into a very fancy looking graph. But instead of using the one in the textbook, I prefer looking at something resembling the structure of this graph. So, all right, let's just, given this problem set, what we'll be working with when n equals to 4, this is sort of a toy example because I wanted you to see what a perfect matching would look like in a graph. With that, we can like relate it to more other NP problems. You're given these pairs. Okay, the first column is like everything in like one group or dimension, if you want to think about it in dimensions. The second column is the second group, and third is the third group. So I draw an edge between every like compatible pair. This is the graph from these tuples. So 2 and 1, here is 2 in the first group, 1 in the second, and then 1 in the third, 1, 3, 4, 1 here, 3 here, 4 here. Hopefully this isn't too confusing. And feel free to pause the video right now to work on finding a perfect set of triplets, like try to assign these edges or like choose edges or vertices, however, whichever works for you, and try to figure out if you can come up with exactly n. So n equals 4 in this case, triplets, such that everyone is happy and we have a 3-dimensional matching. Perfect. Okay, well, feel free to pause the video, but I'm just going to show the answer. So this is what we have. There's obviously sometimes more than one answer, but we just wanted to find out, we just want like a yes or no answer. Like we don't have to be like, okay, so this is exactly the pairing. Maybe sometimes they ask for it, but I think the most important thing is still just like, okay, like is there a perfect matching? You know, we do have a perfect matching using, whoops, these edges. I also am using the erasing tool. And as you can see, each node is only in one triplet. In this case, it's represented by a path only once. And each like pairing, as in each of these edges, is only in one triplet. And something cool to see here is that if I delete these triples one by one, my graph is gone. So if I start with 2 and 1, this path, if I delete this path, it's gone. 1, 3, 4, that's gone. So I have no like redundant edges or vertices left. Back to the problem at hand, we were talking about reductions. Yes. So how can we reduce this problem to a set cover? A set cover up here, I think. Oh, okay, this is like a very, very toy example, and this is like the perfect world. But the problem statement for a set cover is that given sets whose union, like in this case, it's like 1, 2, 3 is one set, 4, 5 is one set, and their union is equal to the universe given here. So what you want to do with set cover is that you want to find the smallest subcollection of sets in S such that their union is the exact same as the universe. And this is actually NP. Intuitively, we are going, because we want to find the smallest subcollection of sets, we have to like go through all the combinations of these sets in S and find the smallest one. So that's like an optimization problem. And intuitively, like you are choosing between whether or not you want to keep the set or not, right? So that's like binary problem, like 0 or 1 for each set. So you get like exponential, hence NP runtime. All right, cool. And this is like the perfect world. Like you use every single set in S without like any extras, and there's like no overlap whatsoever between the elements in S. And then they eventually union to the universe. So how can we like reduce the 3D matching problem to set cover, right? So in the 3D matching problem, we are picking triplets. Like the way to think about it is that we're picking like triplets such that they cover all 3 n members. And in order for us to enforce the rule that each member is in exactly only one triplet, we can only pick n triplets, right? So for set cover, I don't know if you are super familiar with this, but you can actually set a budget. So for example, I can set the budget to be 4 in this case, and we would only be picking 4 sets. So how can we pick the triplets given in our set T, such that we only have to pick 4 of them and they cover all of our elements? So this is exactly a set cover problem, because we can set the budget of the set cover to be n, and we're picking n exact triplets such that they cover all 3n of our elements. And if those n triplets cover all 3n elements, then voila, we have a perfect 3D matching set. So that's basically the intuition. If we wanted to be more rigorous in our argument with this, suppose that we have a solution M that is solution to the 3D matching problem. And we have the size of M being n. So solution of 3D matching problem means that we have a set of like n triplets such that they represent the perfect pairing. And we know that every triplet in n is actually distinct. So there are no like intersections at all between every single pair, and they're like pairwise disjoint. And of course, the elements in M, let's say, if that is a legal way to write this, and their union actually form a set of 3n elements. And it covers the universe. How do I write this? The universe. Like all members participating, I guess. So if we convert all these like tuples or these triplets into sets, then this M is also a solution to a set cover with budget n. So by budget, I mean like maximum sets that we can pick in set cover. Cool. We have to prove the converse as well in our reduction problem. Like when we solve, I know that we reduce 3D to set cover. So we have to show that with a set cover solution, we also can transform that solution so that it is a 3D matching solution. That direction that I just said is essential, but I just wanted to show this other one just for symmetry. Yep. So this is the very important one. This is the one that you need when you're doing reduction, because you're always reducing to like a harder problem, and you want to make sure that whatever problem you reduce to, after having that solution, then you also have a solution to the problem that you reduced from. All right, so let's assume that S is a solution for set cover. And this is very similar to what we did here. So all the elements in S are actually pairwise disjoint because that's like the definition of set cover. And they are also element-wise distinct, meaning if you had a set of X, Y, Z, and a set of X prime, Y prime, Z prime, then these are not equal to each other. The y and y prime is not equal to each other, and the z and z prime are not equal to each other. So this is actually great because once we convert each of like these sets in S to be a tuple, it's actually a solution to our 3D matching because every element is only in there once, and like the union covers all of the elements. Wanted to also like do the reduction of 3D matching to subset sum. So I want to leave that as an exercise. So remember, subset sum is when you're given like, it's kind of like knapsack a little bit. Those two also reduce to each other, just a side note. Given like set of elements, you want to find by selecting like a set number of elements if you can sum to this given number. I was talking about like two sum and three sum earlier. So two sum is easy, but not three sum or beyond. So the way we reduce 3D matching to subset sum is that we have to think about every dimension as in this dimension, and third dimension. They partition a space, and this space has exactly 3n slots, like exactly that many. And ideally, like each slot is like is reserved for each of the 3n elements. So when do we have perfect 3D matching? It's when we have 0 empty slots. And notice how this is like the equivalent of saying there's exactly one element in one slot. And you might think that this is a graph problem, but it's actually not. A few other hints I would give is think about vectors and think about specifically binary vectors. And think about like bitwise operations, specifically like bitwise adding. And also combine that with what I said about each element having their assigned slot, and see when you're given a subset of the Cartesian product, see how that plays into it. It's actually a really cool reduction. Very neat. All right, I think I am out of time here. Hopefully that introduced some interest into reduction. So I think the first step in mastering reduction is to know all these problems by heart. Like what's set cover, what is vertex cover, what is 3-sat, 3-colorability, subset sum, Zoe, etc., etc. I think the chapters in the textbook really helps. Hopefully y'all had a restful weekend. Happy November. Happy daylight savings. And wow, it's November already. All right.
All right, so in this segment, I'm going to be going over a different reduction. This time, it's going to be between 3-sat and independent set. So we're trying to find reduction from 3-sat to independent set. So 3-sat, or stands for, this is short for 3 satisfiability. And it basically means to find a satisfying truth assignment to a Boolean expression that, now in 3-sat, a Boolean expression has this specific form where we have a set of clauses. Remember, each of these is called a clause. And the reason why this is called 3-sat is because every clause has at most 3 literals in it. So this clause is saying X or Y or Z. This clause is saying X or not Y or not Z. And then you can think of X, Y, and Z as being Boolean variables. You have all of these clauses inside, within each clause, at least one of these Boolean literals needs to be true. And then we need at least one true literal from each clause in order to find a satisfying assignment, in order for this whole expression to evaluate to true. So we just need to find, there can be multiple satisfying assignments. We just need to find any of them. So let's say for this one, we can let X be true, Y can be false, and then Z would be false. So if X is true, then that satisfies these two. And then when Y is false, then it satisfies this last one. And then when Z is false, then it satisfies this second one right here. So this is one example of a satisfying truth assignment. So now we have this other problem called independent set, which is basically saying we're given a graph and then we're given an integer k. And then we need to find a set S of k vertices in a graph such that no 2 vertices in S are adjacent. So no 2 vertices in S share an edge. So one example here is we can have, let's say this vertex is part of our independent set. And then let's say we were trying to find 4 vertices that are part of an independent set. We can find that. We can select this vertex, and this one. So you can see these 4 vertices. We have these 4 vertices, and none of them share an edge as a where both of them are endpoints. So that's the independent set problem. And now when we reduce to from 3-sat to independent set, what we're doing is we're saying that independent set is at least as hard as 3-sat. So we're saying that 3-sat is at least as hard in polynomial reduction. So 3-sat reduces to independent set, which means that independent set is at least as hard as 3-sat. So 3-sat is known to be one of the fundamental NP-complete problems. So in essence, this is proving that independent set is also NP-complete. That's more of a topic we'll get to later, but first we're just going to show this reduction. So in order to reduce 3-sat to independent set, we need to show that given any instance of 3-sat, given any possible input to 3-sat, any problem, then we can reduce it to an instance of independent set. So I have here, I've reproduced this same example. And now we're going to try to change this problem into an independent set problem. And we're going to show how to do this, perform this reduction in polynomial time. So the first way I'm going to start is I'm going to create a triangle for each clause where the vertices of the triangle correspond to literals. So where each vertex is a literal. So for instance, here we have x, y, z. That's one clause. So we have x, y, z. These are all nodes in a graph, and then we'll create a triangle from them. X bar, y, and z bar. So not x, y, and z. These are all also three connected. X, y bar, and z bar. You can see that if we try to find an independent set in this graph, then we can see that within each triangle, we're only allowed to pick one of these. We're only allowed to pick at most one vertex from each of these triangles, because you can't pick two or more vertices from these triangles, because then the vertices won't be independent. So we're picking at least one, so we're designating at least one of them to be true. Now note that in 3-SAT, there can be more than one literal in each clause be true, but for the purposes of this reduction, as long as we find an independent set where the size of your independent set is at least 4, or at least the number of clauses, then that would guarantee that at least that we're selecting one of them from each clause. So the important thing is that at least one from each clause is true. Now, this alone isn't going to work. We need to connect these somehow. We need to make sure that the other restriction we need is that something like if x is true, then x bar would not be true. So we need to make sure that the truth assignments are consistent with each other. So step 2 is to add an edge between any literal and its negation. So if we have a vertex x and a vertex x bar, then we always want to have an edge between them. So that means that we're basically enforcing that both x and x bar cannot both be true. Now, it is possible for one of them to be true, but we don't want both of them to be in our independent set. So, okay, so let's do that. So we have an x and an x bar here, so we can connect x bar to x, and then we can connect x bar to this x right here, and we have another x bar over here to the side, so we should connect x to x bar here, and then we should also connect this x to this x bar. We need to make sure that every single possible one of these types of connections are made. So again, I'll do this for y to y bar, y to y bar, and as well as this other y bar here. And then finally z, so z to z bar, and z to z bar. Okay, so that might be a little bit messy, but this is our graph where we've ensured that from every triangle, at least one of them, at most one of them can be in our independent set, and we can never have both x and x bar be in our independent set because those two vertices are not independent. So this is actually enough. So if we solve, let's just say, let this graph be G. Solve independent set. With k equals 4. Or more specifically, I guess, or I guess more generally, we should say k equals the number of clauses. So here we have 4 clauses. Remember, a clause is just every one of these statements. So here we would let k equal 4. Now, when we do a reduction, we need to make sure of 2 things. We need to make sure that every solution to the original problem also has a corresponding solution to the new problem, meaning if there's a solution to the original problem, there's also a solution to the new problem. And then every solution, or if there's a solution to the reduced version of the problem, then that also means there is a corresponding solution to the original problem. So we need to show that these problems are basically solving for the same thing. They're sort of disguises of each other. And we can do that because first, let's go one direction. So let's say if we had a solution to I, then that corresponds to an independent set in G. And we can show that it's true by saying, okay, well, if we had a satisfying truth assignment, like let's say x equals true, y equals false, and v is false, then we can circle a corresponding node. So we know that in each of these clauses, there's one of these, one literal in each clause that is true. So in this case, it's this one that's true, x is true, and then y is false, so this last one is true. And then we can circle the corresponding nodes in the graph. And then we know that this set will be an independent set because we know that this is consistent. We never circle 2 nodes that are negations of each other because this corresponds to a truth assignment. And then we're only circling at most 1 in each clause because that's all we need. We only need 1 true statement in each clause to be true, and as long as we circle that, then we're good. We have an independent set of size 4. And similarly, if we have an independent set in G of the required size, then that corresponds to a satisfying truth assignment for the 3-SAT problem, because when we have an independent set, we can set each of the literals in the set to be true, and then that would correspond to a valid solution to 3-SAT. So here we've shown that 3-SAT reduces to independent set, which means that the independent set problem is at least as hard as 3-SAT.